Yeah, so I'm happy to introduce Parisa again to give a second talk
Yes.
in my departments. Yeah, and if you was in her like earlier talk in 201, it was awesome. Yeah, and I believe this is like more technical version and also extension of those work. Yeah, so Parisa is a professor at MSU and then visiting UCLA this quarter. So if you have any question, want to have more discussion, collaboration, you can find her here. Yeah, and I have an overlap with Parisa when I was a PhD student, and that time she was a postdoc, so sort of her at that point too. Yeah, so without further ado, yeah, let's welcome.
Thank you so much, Kari. Yeah. Yeah, thank you very much for having me here and the invitation, Kylie, Violet, and it's my great pleasure to introduce part of our work on uncertainty reasoning in my lab. So the previous work, actually, the previous talk that I gave was on focusing on more vision and language spatial reasoning. So I thought to not be repetitive, I thought to focus on this work. Actually, I usually focus on the vision and language part. So this is first time I'm trying to really put things about this uncertainty reasoning with LLM together and talk about it here. So let me explain what is uncertainty and LLM. Starting with this example, assume that you ask LLM or one language model or vision and language model, what is this image about? And the model says this is a dog and maybe some explanation. Then you ask, what is the probability of this image being a dog? And the model says this is actual answer. It's extremely high, 99%. Now, I'm asking the model, what is this image about? Just mention one label, one word, and the model says dog. And I'm going to look at the token probabilities here and see what was the, because this is the most probable token that the model took. And I see, okay, the model, perhaps this is made of 60% the probability of saying dog as the first token. So I'm giving the model, let's say now the second image and ask the same question, what is this image about? And I got the same answer, this is a dog. And I asked, what is the probability? The model now is going lower a bit, 95%. It's a dog compared to the previous one. And assume that I'm going to get the token probability still a bit lower. You see that there are these numbers like indication of some uncertainty, right? So now I have a question for you. Why you think, what is the source of uncertainty? Why do you think the second image has lower probability when we do verbalized kind of asking the model and also when we look at the token probabilities? Why is that? Any guess? Yes.
The second image has a little bit of cat features as well. Might be confused with the cat a little bit.
Yeah, exactly. It's like beer or a cat could be, but the model actually recognized it well, but it was a bit lower confidence, right? So what is the source of uncertainty then, based on what you mentioned, ambiguity or lack of knowledge? Can I say lack of knowledge? So basically the model didn't see a lot of dogs like that. Maybe this dog was more typical or something. So it's kind of lack of knowledge that makes the model to be uncertain. And then we see the confidence actually goes lower. So we can say this is the confidence of the model and it's lower because of the lack of knowledge. And this is something that is called epistemic uncertainty, right? This is one type of uncertainty that is due to, okay, if I have more data, then I get better information. There is one certain answer here, one label, but I'm not sure what is it, okay? Look at the second one. The image is just for explanation. I'm just going to ask a textual question. Can smoking cause cancer? The model says yes, and some explanation. And then I say, what is the probability of smoking cause cancer? The model says about 50 to 30% of long-term smokers develop lung cancer. Okay, so now I'm asking the question again, can smoking cause cancer? Just mention yes, no. And I get yes. Let's say I'm going to look at the probability, and the probability of yes is very high. So now you see, okay, some numbers again, like 15, 13, like let's say on average 20%, but I have 90% here. So where this uncertainty lies and what is the source of this uncertainty? The main thing is actually we're interested in the probability of smoking causing cancer, and it seems to be 20%. And here we get 90% probability for the answer, the relationship, the causal relationship is yes. What is the source of uncertainty here? Specifically for the main concept, to be more clear. Yes.
Technically, it's true that in some cases, smoking causes cancer. So the answer is cannot be no, but
the uncertainty is about the fact, right? How often smoking causes cancer? It's more based on a statistical knowledge. It's kind of factual uncertainty, if I want to tell it. Or this uncertainty is inherent randomness and like unpredictability that we have for, okay, how often, if a person smokes, how often they will get cancer, or what is the chances that this person like gets cancer. So this is totally different source of uncertainty. It's called aleatoric, if I pronounce this correctly, uncertainty. It's something that is inherent in the problem itself. And now you see, okay, now do you expect alignment here? Like, because before we say, okay, the model is not certain about this being a dog, token probability goes low, and the confidence goes low. But here, actually, this model is very confident, 90% yes, but the uncertainty lies in a different place. So this is factual uncertainty, and the model is aware of that, right? So these are two different types of uncertainty. So when we talk about LLMs and uncertainty, I think one aspect is like to discuss like what kind of uncertainty we mean. The second question is that why measuring uncertainty is important, right? So of course, we want to see how much the decisions are reliable. If I have this image, I want to see a dog and I want the model to be confident this is a dog. If the model says, okay, 60% this is a dog, then perhaps I cannot rely on it. Or if I say, is there a bus from Wilshire to UCLA campus? Of course, there is an answer to this, yes or no. But if the agent or my friend tells me not sure, high probably yes, or certainly not, of course, I like this answer. Like I really want to know the answer, and this certainty and knowledge is important for me. Okay. So this is about knowledge and confidence. We want this because we want to rely on the answers that the models give us, the decisions and judgments that the model gives us. But then there is another aspect to this. Whatever source of uncertainty that we have, is it epistemic? Is it allotornic? Basically, I want to reason based on that. I need to make a decision at the end, right? For example, here, what does it mean to reason? What are the chances of raining today? 60%. What are the chances that the bus is not operating if it rains? 99%. Now, are you going to take the bus today? Are you planning to take the bus? How did you, perhaps you do some computation, okay, 60%, I don't know if you exactly do this, but in total, there is a high chance that you cannot take the bus because if there is raining, forget about the buses, right? So you say, okay, I don't go. But if I see like 20%, like buses operate, they are robust, whatever happens, though the chance of rain is high, still the bus is 12%, then I'm going to say yes. So this is really like reasoning over uncertainty. Whatever source it is, this is kind of, again, kind of is kind of inherent, right? Aleatoric uncertainty, but I need to reason about it. Sometimes it's kind of, okay, the knowledge of the model is lacking. Again, I have uncertainty. So everyday decision-making, reasoning in scientific domain, clinical decision-making, people having this genetic property, 20% have diabetes, people have 20% diabetes, 80% getting cancer. Now you want to see how probable is this person getting cancer. So I need to do reason over this uncertain information. So based on that, what are the research questions? So this is a research that my student Darius Nafar is leading, and my collaborator Brent Venable and Zijun Kui at MSU and IHMC helping. We are asking these questions. I'm not going to answer all of this, just the three on top. Can LLMs reason over uncertain text? That is the first question. Second, can we mine factual uncertainties, like what is the probability of smoke causing cancer, from LLMs as a source of knowledge? Can we use them? Then in the multimodal setting, also, if there is uncertainty in my perception, can the reasoning over uncertainty help me to make better decisions, right? And then there is other questions like, can LLMs capture these probabilities or uncertainties from in-context information? I will give some insight on this, not talking a lot about it, but related to something that we did. And then the last question, should the token probability, we talked about that, should it align with this aleatoric or epistemic uncertainty? Do you think, that is a question for you, I'm not going to answer that. Do we really want them to align? And in which case we want them to align with this token probability, okay? So let's talk about reasoning over uncertain text first. This is question 1. We started this work a few years back, and then we were looking at some reasoning problems, and this is 2019, this rule taker, something AI2 was creating on logical reasoning, like David is big, if someone is big, then they are green, then if someone is green, they are round. Now the question is that David is round, is it true or false? That is totally logical reasoning. Now, if I have facts and rules that are not certain, David is big, I know, but usually if someone is big, then they are green. So usually makes it a bit hedgy, right? So it's basically some uncertainty there. Normally, if someone is green, then they are around. Now I see, is David round? Now I cannot answer for certain. I need to really give some probability to it, like 72%. Okay? So this is the problem. We try to create such a problem and evaluate the reasoning over text. This is the problem setting. So I have the context that is facts, like David is round or green, and then we have a set of rules. The rules can have probabilities. So the rules is like some premises, this person is this and that, then this person will be round with the probability row is some value between 0 and 1. So one property of this data set is that the rules are context specific. So today I'm telling you, people who are green, they are happy. Tomorrow we say people who are green, they are sad. But you have to use the rules and reason based on context specific rules, right? So that is one thing. And then the answer will be the probability that is actually a numerical value of the probability of the question that we are asking. So the answer will be something between 0 and 1. So this is the problem setting that we try to create. And then what do I mean by reasoning? I showed you already example about the boss and raining. This is something taken from the data set. Before us, actually, there was a rule BERT data set. It was 2018 at the time that BERT was coming out. And then they had this 1 year later, they had this rule BERT. So this rule BERT, the difference is that the rules were not, actually there was probabilistic rules created and a data set with those, but the rules were not context specific. They used Wikidata and then they got some rules like this. If A is a spouse of B and C is a child of B, then high probably, let's 90%, C is child of A as well. Right? So that is kind of a rule that holds everywhere. And if A is a cousin of B, then it's low chance that they are married, so 15%. They just got this data from Wikipedia and computed the probabilities, and they formed this data set. But then if you feed this data to the model and train it, the model captures these correlations, right? It doesn't need to have the rule in the context because the rule is not context specific. But that is not what I'm trying to solve. I really want the model to look at the rules of reasoning, and every time the model does the logical reasoning, not learning the knowledge and apply it, but really doing the logical reasoning. That is why in the second case, you see our example that I explained already. But then the type of reasoning that we need, or the type of low-level computation that we need is as follows. If the fact 1 is kind of 100%, then I'm applying a rule that has 90%, then the outcome of that rule will be 90%, like 1 multiplied by 90%. So basically here, if I say David is big, and usually if someone is big, they are green, and usually is a 90% probability, then David Green will be 90% probable. And then if I have 90% and green, and then normally they are round, and that is 80%, then the probability will be 90 multiplied by 80. I will get 72% probability that David is wrong. So we expect the models to really go through these steps of probabilistic reasoning to give me that number, 72%. Okay. So now how the question was how we should do this. You can train with this data that we created, synthetic data, just train the model, new information. But actually, we tried to do some training. This is the time of BERT-RoBERTa, like encoder-based models. And we wanted to tune the models to follow these rules of probabilistic reasoning. So we define an objective, new objective for the training. And this is the following. When I have a specific rule, this is synthetic data. So I have the control. I can have all these intermediate facts and their probabilities all laid out and stored in my data set. So I can get sorts of supervision from this. And for each step, I'm going to have like probability of the outcome minus probability of the premises should be actually multiplied by the probability of the rule should be equal, right? Because if I have like this fact 1 multiplied by this, then I get the probability of the outcome. So these two sides should be equal. They should be consistent. So with that rule, we can get a bunch of consistency constraints between the outcome and the intermediate probabilistic facts, and we try to push these probabilities to be close to each other, apart from the optimizing the task, which is answering, getting the actual value, right? Question?
How do you choose?
This is data set that we created. This is synthetic. So we actually use the rule taker, and we make a kind of probabilistic version of it, and we use some tools to compute the outcomes. And now we have the data set there, so we can use it. Yeah. So we do actual probabilistic reasoning to get this, and then we put it in the data set. Yeah. Okay. This is basically the objective. I have the task loss, whatever it is, cross entropy. In this case, you can even do regression loss because you want the actual value. But here we can also have this violation from these probabilistic rules, all the intermediate facts to be summed up and being a part of the loss. At inference time, we don't need to, because we don't have these all steps, like the question you asked, right? We don't know like what are the exact rules. We don't know what are the probability of the intermediate facts. So at the inference time, the model just doing the task end to end, but we hope that the model captures these computations or reasoning line. So these are some experiments that we did. We call it PCT, probabilistic constraint training. Does PCT helps the probabilistic reasoning? Can we get the correct intermediate facts and their probabilities? If we train in this synthetic data, if I map it to the rule-bird data, can I transfer? Question.
I was just wondering, the previous slide you had the constraint. So what is it the amount of times that the model violates the constraints that you set that is in the loss, or how is that tested?
So basically the loss is the difference between the probability that is generated for the fact based on the computation and the probability that the model generates for each fact. So, and we have some, okay, how to measure this? As I mentioned, there is like a little bit of work was there, and they were evaluating mostly on binary. Like I'm going to say like the question I'm asking, and if the probability is above 50%, the answer is yes, below 50%, the answer is no. So it was not really evaluation on fine-grained the actual value of the probability. That's why we introduced some new metrics like we call this accuracy at 1. So if the difference is 1%, we say this is accuracy. This is very fine-grained. And constraint satisfaction. So constraint also is probabilistic. If the constraint is like satisfied with a certain threshold, then we say, okay, this is satisfied, otherwise we say no. So we measure both satisfaction and kind of accuracy of the probabilities generated. And at the time, as I said, our training was on these encoder-based models. But then we saw as we were doing this GPT 3.5 came out, GPT 4 came out, and we were comparing just with the prompt engineering with those models to see how it works. Some of the results, if I want to share, this is basically the data set has different depths of reasoning. And here you see D1 to D5 is like more steps of reasoning is needed. Roberta, actually, we realized that in the rule-based paper, they put the rule in the context, and we realized actually if we remove the rule from the context, it works better because the rule just makes the context longer in the text form. And with BERT, Roberta type of models, the rules really didn't help. But if we do train with PCT, then you see the darker is the better. So you see a little bit of kind of variation in the results. Sometimes it's not consistent, but you see a lot darker points here when we use PCT compared to just using the rules in just asking the model. Yes.
I just wanted to understand what's the x-axis, like what are the columns of?
So these are accuracy at 1,
Okay.
and these are like depths of the reasoning. So I need depths 1, I need 2 computation, 3 computation, and 4.
So like the 5 columns that you have, like they're accuracy at
Okay,
1.
so this is okay. Sorry for missing that. So this is basically the models. I think this is the models that are basically trained of M1 to M5. It's 5, right?
Yeah.
Yeah. So it's basically we have the models also trained on D1 or models trained to D2 and so on. And then here is rule taker pro data set. This is basically again the same with our data. This is with RuleBird, but this is with rule taker pro. And then we saw again when PCT, you see a lot of darker here, and the model is performing much better when training with PCT. This is one result. But then there were multiple questions with depths of reasoning, how the model kind of with complexity of the question. And maybe I highlight 2 things here. One is domain transfer. And the domain transfer is like I train with my rule taker pro because I created this data set and I'm going to test on the RuleBird. And I see actually here you see again, when we pre-train with the PCT, the transfer happens and the model gets better results compared to just augmenting it with the new data or not doing just the baseline over time. This is one result. Another, you can also see at the time, like this is GPT 3.5. You see that? And you see GPT-4 also was failing. And GPT-4 3.5 star is actually chain of thought reasoning. So you see that all the models performing very badly. Roberta still is doing better when trained with PCT. Okay.
One more clarification question just for the rule taker data set. Like you mentioned about how usually and normally and seldom might have some associated probabilities. Are these information like known to the model, or is it something which?
So we have two versions of the data set. One is with the exact numbers, one with the hedge words. And actually we use this linguistic studies with the human, and we got these numbers from them. And then when we use like hedge words, like usually, normally, the computations are done based on representation of usually, normally, and the model captures that. And actually there was 1 or 2% better performance when we use hedge words compared to the numbers. Yeah. That was interesting. So the outcome of this work, it's kind of a couple of years ago, new data set we created, RuleBird, Rule Taker Pro, and then we had this probabilistic constraint training. Then pre-training helped transfer, and generative large language models were poor, at least the time that we tested them. Okay. Oops, sorry. Okay. So now the second work that we did, this is AAAI this year. Now we try to say, okay, that was training paradigm with the small models. We try to do something at the inference time and also try to extend the data set to make it much more complex. We started from Rule Taker and we made Rule Taker Pro, but here we started from scratch, trying to actually generate Bayesian networks and explain the Bayesian networks in the form of text. like G event is true with 40% probability, P event is true with 20% if G is true. So we try to explain like a condition, like these Bayesian networks and conditional probability tables. And that was our text. Now we have a query that we wanted to ask, what is the probability of event P? Or what is the probability of event P given G happening? And now we want, again, the same setting. We want the model to give us this numerical value of the probability. So that is the setting. Here is the way that the data look like. So I have these graphs, these CPTs, and the text that is related to this explanation of these CPTs. And these are basically the queries, exact probability numbers, like we basically want those to be generated as the answer. How to create this? This is a data set called Blind. As I said, it's AAAI. You can see all the details of how this is generated. We have like a bunch of variables. I think if I remember correctly, we tested until 10 random variables in a network. And then we have these all configurations of possibilities, how these variables are placed with each other. And then we generate the conditional probabilities for each of them, right? Each node, this is the root. These are basically, and then the queries are variety of queries like probability A, B, C, just marginals, conditionals, P, A given B, and so on. And we have so all of these are there. And we have the kind of context and question. Context is basically the explanation of the Bayesian network. And the question is, what is the probability of B being true given that D is true? We do the textual form. And now we also have this PG and Pi, these probability graphical models in Python that we can actually compute all these queries, answers, and have the ground truth there. So the data set is textual context, query, and the answer, which is numerical values. This is the data set. And here, as I said, we don't want to do tuning or training or anything. We just wanted to see evaluation of the large models and try to do something on the in context engineering or mapping to the formal solvers. That was the main idea. So here is an example of like how this looks like. So you say basic QA is like, okay, I pass the information to the model and I'm asking the question, like solve the following probabilistic question and generate the probability of the answer by only providing a number. And then the context was what I showed you before, and the answer is 8%. Now I say in the chain of thought, solve the following probabilistic question, provide the detailed explanation of a mathematical reasoning at the end, write a sentence that will give the final answer rounded in one integer. And the model gives you 8, for example. Okay. So we saw that actually, you saw also some of the results in the previous experiments, but with this data set, it even was more severe. There were a lot of mathematical errors in the chain of reasoning, hallucination of numbers that are not in the context appear in the reasoning, and then complex reasoning was really difficult for the models. We could extract the probabilistic information and then do the dependencies extraction, and then try to do like kind of inference. That is one like methodology that we are going to follow and see how this can be possible. So the main approaches here is that program-aided language modeling, try to just pass it to Python or pass it to an algorithm, Monte Carlo algorithm, or pass it to some probabilistic logical solvers like problog, and then try to do that. And there are subtasks like, should we do extract again the numbers first and generate the graphs explicitly and then try to create the programs, or we just do it directly? So there are some subtasks here involved. So let me explain some of the settings. So green event is true with probability of 80%. Then basically we expect the model to extract this in Python code. This is the PAL setting. And then we have green event with probability of 20%. We expect the model to extract this in Python code. And we expect it actually in Python code, we expect all these summation, multiplication, divisions, low-level computations for this marginalization, conditional probability computations. We expect the model to write them in Python. It's a bit ambitious, I guess, right? But that is the test that we try to do. In the Monte Carlo algorithm, we try to actually get the model, know the structure of the model, now go to do like kind of walk through the network and do sampling and collect the likelihoods. So this is again, these are fed to this program and we do the sampling. Problog, I'm not sure if people are familiar with Problog. Problog is a declarative probabilistic logical programming language. And you have facts and rules, and then you have probabilities assigned to them. And as far as you have this, the Problog can do probabilistic inference, probabilistic logical inference for you. So this is interesting because Problog is declarative. It doesn't care about the underlying computations or what is the inference algorithm, right? You just declare the facts and rules and query, and it just takes this. So it's very close to natural language, right? So if you are able to map to Problog, then we are done, right? And it seems the mapping is easier because this is much higher level than Python code, right? Okay. So some of the results, this is not with the PAL or these techniques. This is more basic question answering, few shot setting, zero shot, and yeah, that is with basic and chain of thought. So you see the results are really low. This is with GPT 3.5, Llama 3, GPT-4. This is again the number of nodes. V is the number of nodes. This is average of 2 to 5. These are on the less complex side. 6 to 10 is the higher complex side, and this is the average of 2 nodes until 10 nodes. So you see that with 2 nodes, perhaps the models do something, but the rest is actually not that much meaningful.
Are these like percentages, like accuracy percentages?
This is again AC1.
AC1.
Yes. So it's very strict evaluation. So you see these are really, few shot even made it worse because the context became longer, it became even worse. Yes.
One quick question. This is actually another clarification. You mentioned 2 ways. One is a Python code.
No, this is just basic. This is none of those. This is the baselines, right?
Which is text in directly the probability out.
Yes. Yes. About the chain of thought and few shot and so on. Yes. But here, the next slide, so this is just wanted to highlight the weakness of the baselines. And this is basically when we apply the techniques that I showed. So this is PAL, you see, PAL is doing something 66%, B3 is still 34%, but then it goes very, very low. We have this, how you read this with a node extraction. If we do the extraction of the node and how that helps, it seems that it helped sometimes with PAL, especially it helped. And then we have the Problog, and you see as we go down, basically GPT-4 doing much better. And here also, you see that if we have lower number of nodes, there is darker, so the accuracy is higher. And all the time, Problog seems to be much better compared to the other paradigms. And PAL was really performing lower. And I think it's expected. It's really low level. The gap between the problem and the solution code is really large. Yeah, you see all these patterns here. Okay. So the outcome of this analysis of LLM's limitation, probabilistic reasoning, in the probabilistic reasoning. And then mapping to symbolic methods. This is synthetic data. Okay, I get that argument. This is synthetic data. Mapping to this is hard, even if you have more natural data. But if you can map to symbolic, then do symbolic reasoning. That is one better solution. And we have this data set blind with these Bayesian networks that helps the evaluation. So now this was a bit, it was more evaluation and see how different kind of techniques can help to solve this. But the setting is not realistic, right? Because full Bayesian network in the context, who has this at all? Like in any domain, if you want to sort, like infer what is the probability of this person getting cancer, there are so many parameters are involved. Each medical paper might have really one investigating 2 variables correlation, let's say. but now we want to have all the involved variables at one place in the context, which is not realistic, right? So then I think a more realistic setting that we moved on, let's ask the language model itself to get those CPT values and do the inference. So the question is, question 2, can we mine factual uncertainties and probabilities from LLM's internal knowledge? That is the question here. So here we have this, why Bayesian network? We wanted to actually build these Bayesian networks because we think if we have for each domain, we have this Bayesian network that helps us to solve the problem. So it's really kind of explicit reasoning and useful. It's a powerful formalism, can deal with the uncertainty in a principled way. And then, but the problem is building them, right? Building these Bayesian networks and even explaining them in text, let alone that is fine, but building them, how we can build them from the whatever sources. Usually these are made based on the data, huge amounts of data that people collect. There are some expert knowledge that give us these probabilities, but there are also combination of the both that can be used to do that. And here we actually try to see if the internal knowledge of LLM can play the expert role to give us some priors here. That is the main idea. So again, go back to my first slide a bit, like to talk about this factual knowledge. This is where was Einstein born, and then there are this kind of uncertainty in the information, is kind of lack of knowledge, epistemic uncertainty. But here, actually, this is what I want. The factual uncertainty that I want here is something that I'm interested to see if the language model can give this to me. So LLMs, we want to see if they can approximate the expert priors. And then we also want to map this to Bayesian networks because Bayesian networks are very good paradigm for doing uncertainty reasoning, but building them is hard. So those are basically the motivations. So the problem setting here is as follows. It's kind of similar, but we want to have this graph is given. It's not similar actually because we don't have text here. We have this graph, Bayesian network in terms of nodes and edges, and then we want to estimate the CPTs, the probabilities. We want to estimate those. So one assumption that we make actually while we're doing this work, there are some works done in parallel. And we saw that some people work on the structure already to see how they can get the structure. But in this work, we wanted to really make the problem simpler to be able to evaluate. So we have basically, we assume the structure and the involved variables are noun. So basically, I know that smoke is relevant to cancer. So I want to get the CPTs. So we just want to get the probabilities, and we are in discrete settings. So all these variables have discrete values. So here is the approach. So we have this basically, what I want to see, if a smoking causes cancer, what is the probability of doing that? So we try to actually look at every pairwise variable and ask a question, like what is the probability of like smoking causes cancer? And we try to ask the LLM to give us this estimate. So there are different prompt engineering approaches. This is nothing fancy here. We can separately ask questions independently from LLMs. If I have a CPT of 10 nodes, I can just ask for every cell in my CPT, I can ask a question. But I also can give the knowledge to the structure to the model and tell the model, give me all the probabilities of this CPT. That didn't work actually. So the separate states, the separate states name, is that we are asking like single questions every time and get these probability values. So this is basically, we get this information, like what is the probability of lung cancer is true, given smoking is true, what is the probability of lung cancer is false, given smoking is true. So it's for every single cell in the CPT. Now, the main idea is that, okay, we did actually a lot of experiments I will show you. So this basically, the initial information that you get with prompt engineering was not very reliable. So we had to go to the normalization. It was not even normalized. So to really make sense of the values that are generated. But then we thought this can be used as priors maybe, because as I said, for building the spatial networks, you need huge amounts of data, realistic data. But if I have little data and I can really do some likelihood estimates from my little data, and I can use this LLM's internal knowledge as a prior, then I can use these smoothing approaches and combine the two sources of information to get these CPTs more realistically or more useful. So that is basically the main idea. I have these priors from LLM, 75%, 25%. I have the likelihoods coming from data sets. And then I'm going to just smooth with some alpha parameter. I can weight the LLM more or LLM less, so I can really adjust that and compute these priors based on the combination of the two sources of information. We call this EDP, extracting probabilities from the expert or expert-driven priors. So the good advantage of this work was that we found actually 80 Bayesian networks that were realistic. There were even problems like classification problems that solved based on this repository. So we had ground truth Bayesian networks, and we could do KL divergence to see how estimates are correct. We can have also F1 accuracy of the classification that is based on this probabilistic network is done. We can actually see how the impact of this is on the downstream classification. If I have inaccuracy in the estimation, still we can have the effect on the downstream. We have a lot of baselines, like how these probabilities, if you just give nonsense, get some random probabilities from the LLM. If you give context, explain each variable, what happens. If you don't give, explain the variables. If you look at token probabilities, I'm going back to this question, do we expect the token probability to be aligned with these values that I get? Perhaps not really here, right? But we did that experiment also to look at the token probabilities. And then we do this maximum likelihood estimates based on only the data, using prior as uniform as prior. So there are a lot of variations and baselines that you can see the details in the paper. Here is the baseline. So GPT-4o, GPT-4o mini, these are step-by-step just querying the language model. So these are really querying language model with different prompt strategies compared to uniform. So here, this is KL divergence. So the lower, the better, right? And you see that overall, basically, the separate state is better than when I'm asking overall, the purples are the full network is queried. They are better. So these are really just the baselines. And our goal was to see if EDP can help. Here, there's no combination result, but this is just the models and how they operate, each of them. You can compare different language models here and how they give us this internal knowledge with this prompt engineering. But here is more interesting. So we have this data that could be, if I have 10,000 data elements, now maximum likelihood can give me perfect estimate of these CPTs. A combination is similarly good. If I assume uniform priors, still I'm good here. But if I'm going to reduce the data, you see here I have 10 samples, 3 samples, and so on. So I reduce the number of samples, and I see, okay, now EDP is getting me better results. At least we are looking at the medians, actually. So if we look at the medians, we see that EDP is giving me much better results compared to maximum likelihood. Sometimes there is discrepancy, but overall, you can see that as we go little data, the EDP gives us the combination, the orange gives us a better result compared to likelihood or uniform priors. This is the effect on the downstream classification task. Also, I mean, the structure, actually, there are papers on these Bayesian networks. And these papers, we try to go to the papers, get their data, and use the data and run the classification. But in those papers, most of them try also to do the structure somehow. Sometimes they do naive-Bayes assumption. Sometimes they use these hill climbing approaches to learn the structure of the Bayesian network. And then the structure here is fixed for us. Whatever approach they use, we just use that to get the structure. And then we try to do this estimation of the parameters on our side. And this is the random and chain of thought. And we see that this is basically just querying the language model. But here is basically the EDP usage, and you see that EDP and maximum likelihood, we always see a little bit of improvement with EDP compared to the maximum likelihood. That is basically, that was very interesting result to see here. So the outcome was basically, we did this 80 Bayesian networks with the, as a ground truth, we brought the classification task related to these Bayesian networks also into play. We combined LLM priors with the data, and we saw that we can get better accuracy for the downstream classification tasks, and also the KL divergence of the parameter estimation is better when we use LLMs as priors. The last, like maybe 3 more minutes, I think I talked about this work in my other talk, but I wanted to mention this because I want to highlight the probability and the uncertainty usage in this work. So this is basically for compositional reasoning, and the task is like, how many blue squares are to the left of the large red sphere? The original problem doesn't have any like kind of probabilities or anything, right? But when I want to answer this question, this is compositional problem. I have objects, attributes, and their relationships. And now I need to combine the probabilities to get this probability of something being blue, square, and then combinations. Some people, there is a paradigm now in computer vision community, more like works like VisProg started, and then Viper GPT, they map to code, right? They map to code to answer the questions. So now what I want to say here is that, okay, we can map to the code, but there is always uncertainty in the perception. I don't know how probable is the blue, right? That this bounding box is blue, and then I want to combine them. So I want to really deal with uncertainty in combining perception, like let's say uncertain perception with the explicit probabilistic reasoning. So that is the main idea here. So learning concepts and dealing with uncertainty in perception to do reasoning. That is the idea. So this framework, this is also a submission. Daniel is doing that, has been doing this work. So we try to do the from language to Python code, but actually the Python code now asks queries the underlying language models, and it gets some scores. These scores are used as this kind of probability uncertainty measures, right? So for example, I say, is the object in the bounding box a sphere? So I want to see like how many colors of a small spheres are there. So I want to really pinpoint to the concept. I want to see, is there a sphere? Is it a small? And how many of them are there, right? But recognizing a sphere itself depends on the capability of the underlying model and their certainty, right? So that is why here I'm not only asking the model, get the answer and go, but I'm getting the answer, use the uncertainty, and combine these uncertainties to really get to the final answer. So here, how I'm going to combine, what are the solutions? We could do basically map to problog and do that. There is a recent work that actually they did that, Naver, right? This is, I think ICCV 25 or 24, okay. But then, we wanted to do Python, and we wanted to use some soft logic combination of these predicates. Like a sphere X is giving me 2080, and small x, let's say, give me, I don't know, 3070 for small bounding box. And now I'm going to join these two, let's say multiply them to get the AND of the two. And then I get a new score that gives me the joint probability of being a small and being a sphere for every bounding box. And then I go forward with accumulating this probabilistic information and get something that at the end tells me what is the most probable bounding box that applies to this. And then maybe I can then have a threshold and count there at the end. So basically, I think this is kind of interesting because we consider, again, uncertainty in the perception, and we try to do explicit reasoning for making the best decision in the question answering setting, as well as referring expressions. So this is actually, there are some very interesting results. One of the results that I really like is this result on like a data set called GraphGTA. So one thing that is a problem here with the current language models, large language models, is that you cannot really evaluate their compositional ability because of the data contamination. So in the data set that I showed you in the first slide, these shiny spheres and so on, the models perform very well because they have observed everything already. But in this data set, we want the actual composition to be made. And it seems this data set was not very, was kind of untouched by these models. They were really poor in doing this, like interval, 2%, almost 2% accuracy, 8 billion, 7% accuracy. And then we do tuning with the data, we get 32% accuracy. But then if we do, this is Neptune, the model that I showed you, mapped to the NeuroPythonic framework. And we actually see that with NeuroPythonic framework, dealing with those uncertainties, accumulating them, we get to 69. And even with the smaller models, 8 billion, with the smaller models, fine-tuned with the output of the program and tuned, we get higher accuracy. We get almost the accuracy of the 8 billion model. And this fine-tuning, I should mention that, sorry, this was a bit rushing. So the advantage of this is that when we do combination of these probabilities, they are all soft and differentiable. So we can backpropagate the error and tune the underlying VLMs based on that, and then fix them if they are like kind of misunderstanding basic concepts. Because the composition is taken care of by the program, the concept learning should be done with the tuning aspect. So that is basically in the vision. Final takeaway, can LLM reason over uncertain text? That is one result that I showed you. Can we mine factual uncertainties and probabilities from LLM's internal knowledge? We did, as priors, they did better. Combining uncertainty in perception with probabilistic reasoning in multimodal reasoning is helpful. Remaining questions, can LLMs capture the probabilities from in-context sample? This might be a bit different question, but I wanted to mention it because this is relevant to this paper that we did. It was NACL this year. This was more related to regression, very different, but I want to connect this for more insight. Here we put basically X's and Y's in the context. This is regression setting. And we want to see if the language model can really do meta-learning and come up with a function that expresses the correlation between X's and Y's. So similarly, we can do sampling from the data, put the data in the context and see if the model can capture these correlations, right? So that is actually, I see a very recent paper trying to do that. So I haven't seen the detail, but you can look it up, like looking at the LLMs can do the distributions. So, but this is, again, I think relevant to this regression problem, and this is something interesting. We use the MLE separately, but potentially you can put it in the context and see if the model can generalize. The last question, you can answer this. Should the token probability really align with the aleatoric or epistemic uncertainty, or none of them, or maybe depending on the situation, it should align with some of this or one of this, right? So this was about uncertainty. Just give you the context of what else we do in HLR. We do spatial reasoning, compositional reasoning, uncertainty reasoning, and like grounding, language and vision and navigation. We do generic neurosymbolic frameworks for combining this logical reasoning with learning. So just listed this if you are interested, because we are here, me and my students, to establish collaboration. Any of these topics, if you are working on these relevant areas, we'd love to collaborate. And I would like to thank my students working on this again.
We have time for couple of questions, maybe.
Yeah, I think this is really interesting, and I particularly interested in your Bayesian network part of work. One clarification question is, there is a matrix of Bayesian network KL divergence?
No.
Oh.
So I mean, it's not we try to see how to evaluate this.
Yeah.
That's why we try to really do KL divergence, because you have a distribution of the variables,
Right.
and we try to do this metric. But I don't think perhaps a couple of papers use the variation, but it was not very clear to us how to evaluate it.
Oh,
Because mostly on downstream tasks. That's why we added that downstream task.
right.
The first round of this paper, people were confused, what is this KL divergence? And we had to go to
Right.
the classification to see, okay, this is how the more accurate probabilities work. But I mean, you can do MSE, these are a bunch of real numbers, or you can look at them as distribution, do KL divergence.
Right,
Yeah.
right. Oh, yeah, I think it was just purely clarification question. When you
Yes.
say the KL divergence, do you take like every variable, like what are the distributions you take? And then do you take average of the KL divergences?
It's average over yeah, exactly. It's based on CPT
Mhm.
and then the average over the CPTs. So that you have two distributions.
CPTs, I can imagine you can have different conditions, like conditional probability, marginal probability.
Yes,
Or
or
do everything.
the CPT is basically you have this entire CPT. Yes, exactly. Per value, like A0, B1, what is the probability?
Right.
So we have all these possible states and their probability. That is basically the distribution. And it's discrete space here. So we have all these tables.
Right, I see, I see. Another thing I've been thinking is also just try to sort of push this a little bit. I know because like you said it, reviewer bring this up. I have been pondering on this as well, which is a lot of your thing, which is nice scientifically, is in like a synthetic setting, or it's like a setting that is really more of a, you establish the Bayesian network and all that, right? It's a synthetic exercise. I was thinking whether with the data you've already established, I know you have 80 Bayesian network, right? Maybe through fuchsia learning or whatever, do you think it's possible for a language model to learn to actually construct Bayesian network for problems rather than just do that? Not like, I think like if you think about it, right, if we're thinking we can push this and use large language models to solve our, I think a lot of this economics and then a lot of the social science problem, they actually want, and I think a lot of their research problem is to establish a Bayesian network for
Yes.
their problem.
Exactly.
And then do inference on that,
Yes.
right? So in that perspective, it also will serve you in terms of motivating the work to say,
Exactly.
if we establish a full pipeline from the LLM to establish a Bayesian network and do inference on the Bayesian network, etc. So I wonder whether that's something you've thought about.
Yeah, of course. So that is why, I mean, we have Bayesian network is the structure plus the parameters, right?
Mhm.
So the structure here, as I said, there are very recent works actually try to do the structure.
Okay.
And then we try to fix the structure to be able to evaluate the CPTs. Now, if you have a structure and CPTs, you have a model of the domain, right? If I'm a doctor and I know, okay, I guess there is a smoking or weight or age, these are kind of factors. I put them together and I ask the language model, and maybe I have a little bit of data, then I combine, that is main idea basically. Then you will have basically this Bayesian network and you do explicit inference over them. Yes.
Right, exactly. Because another way to view this is a type of chain of thought,
Yes.
but in a much more formal mathematical format, right?
Exactly.
For large language model to solve domain-specific question, and then
Yes.
with much more precision.
Exactly,
right? Yeah.
exactly. Actually, I was in Mila last week's couple of weeks, and I heard that also Bengio had this project on scientific domain.
Oh,
And actually, they tried to extract knowledge from the scientific literature
okay.
and then map it to some Bayesian network.
wow.
Not Bayesian, but probabilistic
I see.
model
Right.
to do reasoning. So I think it makes a lot of sense if we talk about robustness and reliability. It's very important, actually.
And interpretability.
Yeah, interpretability, exactly. That is what domain experts need.
Awesome, thanks.
You, I think.
Oh, okay.
Yeah,
Well,
well,
many other.
Yeah.
No. I mean, I'm here if anyone wants to discuss this. I would be happy to, actually. Thank you so much for the opportunity.
Thank you.
Should I go out?